Okay, I think it's about time. We can get started. Hello everyone. Welcome to attend our system seminar series. So this is our ninth seminar. It will be 1 hour, including 45-minute presentation and then 10 to 15 minutes for QA. If you haven't registered our mail list, please scan the QR code so you can receive our emails for more events in the future. We also have Slack channel for networking and potential collaborations. Our YouTube channel is used to post past events video recording. So please feel free to share it with other people to review if they cannot join online. And then finally, some logistics. So this event will be recorded, and if later the presenter agrees, then we will share it on YouTube. If you have any question, please type it in the chat box. We will moderate the QA session, and the speaker will answer them towards the end of the talk. So, yeah. So today, we are very glad to invite our nice speaker, Professor Ishan Thakkar. He will share with us his work titled "Scaling Up Photonic Tensor Core with Device Circuits Signaling Co-Design." So, Dr. Ishan Thakkar is an assistant professor in the Department of Electrical and Computer Engineering at the University of Kentucky, Lexington, KY. He received his PhD and MS in electrical engineering from Colorado State University, Fort Collins, CO. His research broadly focused on designing and optimizing unconventional more-than-more architectures and technologies for energy efficient, reliable, and secure computing. Dr. Thakkar has more than 55 peer-reviewed publications in top journals and premier conferences. His research contributions have been recognized with 6 Best Paper Awards and nominations from IEEE ACM-sponsored peer-reviewed journals and conferences. So without further ado, let's welcome Professor Thakkar give us the talk.
Thanks, Renchi, for the kind introduction. Let me share my screen. Right, hopefully everyone can see the screen.
Yes.
So, so I'm going to talk about the work that I've been doing for last 3 to 4 years, among other things, and I'll try to sort of give a whole overview of what I've been doing, and then go to some specific publications, and we'll deep dive into those publications. So again, the title was already read before. So the title of the talk today is Scaling Up Photonic Tensor Cores with Device Circuit and Signaling Co-Design. So many of us already know that optical computing architectures and chips are actually projected to have great advantage over electrical chips and architectures, especially when it comes to linear computing, or you can say linear algebra computing, like tensor kernels, matrix multiplication, dot product, and so forth. So the optical computing advantage in this publication, they have basically shown that it is set to become more than 10 to the power 4x compared to NVIDIA's A100 GPU, which is pretty powerful GPU out there. And this advantage is basically realized because of the massive wavelength. I would like to say not just wavelength, but massive spatial processing parallelism available in optical architectures. Sub-nanosecond scale, you would say, start to completion latency, and near dissipation-free dynamic operation. So these are the advantages of optical computing. And with that, they have basically shown that orders of magnitude energy advantage over GPUs can be basically achieved while executing inference tasks of, we can say, modern transformer neural network kind of algorithms. So with this advantage, a lot of groups in industry as well as in academia, they've started looking into prototyping this optical or photonic computing chips and architectures, and there are some examples on the screen. These architectures basically involve variety of devices microring resonators, Mach-Zehnder interferometers. There are some electromechanical devices as well. With this kind of a lot of research going on in this field, it turns out in all these architectures, if we can broadly basically categorize them into two classes. One class is basically that deals with digital operands and does the computing on digital operands, and the other class is analog operands. So in digital operand, people have basically used, can say, the nonlinear spectral behavior or active behavior of microring resonators to actually realize some logic functions like AND gate. And then using that AND gate and then all optical shifting and editing, addition or accumulation, you can actually achieve some sort of MAC operation or a dot product operation. That's going to be digital. Architectures in analog operands, again, analog architectures come in a variety of organizations, you would see. But I've given a couple of examples over here where you can say Mach-Zehnder interferometers can be used to sort of along with microring resonators, or only microring resonators can be used. And the idea is to sort of print, or you can say transduce the electrical operands. You convert them into analog values, and then you can convert them into analog optical signals. And then on optical signals, by transmission, you can multiply those optical signals. And then we can use photodetector, which essentially works as a multilinear map, which can add those analog optical signals to give us sort of signed accumulation of those products that you can basically achieve through transmission, right? So at the end, photodetector can generate those, we can say, dot product results. And then when we parallelize this, like shown in this over here, we can basically show that one balanced photodetector pair can produce one dot product result, and we can parallelize those. So we can have sort of a tensor core or vector matrix multiplication core, or similar architecture we can design. So if we talk about the pros and cons of this, right? So I'll highlight only the most important ones. So if we talk about digital operands, we can typically run them at a high data rate because of the advantages of the optics. We have near impedance free and distance independent bit rate. So the optical digital architectures can run at higher data rate. We can also have parallelism that we can realize through wavelength division multiplexing or space division multiplexing across waveguides. So those aspects are true in both digital and analog, although for analog computing, the speed or the data rate tends to be a little bit lower than the digital computing. The disadvantage of digital operand is if we basically implement that shifting and accumulation in all optical domain, they tend to consume very high area. We have bulky hardware. And we can also have high end-to-end latency, because the nature of we can say digital, it's basically, when I say digital, I'm talking about binary encoded. So binary encoded operands, implementing arithmetic functions on them are basically naturally latency consuming, right? So they can take longer latency. Versus analog computing, we can basically be very fast, sub nanosecond scale latency, and less hardware is basically required compared to the digital operands. But analog basically computing also suffers from, you would say, the noise margin issues. In some cases, you would say there are trade-offs. We'll talk about that later in the talk. But those trade-offs basically limit the parallelism, and the precision also basically is limited in analog computing. So with this broad classification of the architectures, what is it that basically the main advantage I would like to say about analog photonic architectures is this 2 degrees of freedom for mapping. Let's say in this example, I'm showing a matrix multiplication kernel, and we can map the inputs and outputs from the input and output matrices using wavelengths as well as waveguides, right? So you have 2 degrees of freedom for spatially mapping these computations. And we can basically arrange, I've shown microring based. So we can arrange the microrings in 2 different ways at least. There are some more ways we'll talk about later. But in this case, you see these are the microring modulators that imprint the input signal, and then these are the weighting banks, right? So you see there are 2 different organizations of those, and we can actually do the mapping of input values and weight values across wavelength and waveguide. So this can lead to massive spatial parallelism because of this extra degree of freedom, right? But all is not hunky-dory, right? Unfortunately, there are challenges, especially the scale-up challenges, right? So how do we scale? How do we have more and more parallelism, right? But when I say parallelism, I'm really talking about, can we have, if you look at this, there's a basically M weighting banks, and each waveguide here or each weighting bank is basically able to process n optical signals, right? So I'm talking about the n cross m size. Can we scale that? How scalable is that size, right? So in other words, number of waveguides and number of wavelengths per waveguide in a tensor core, how can we scale that? So there are challenges that exist in that regard. So the first challenge I would say is optical crosstalk, obviously. So when we basically cascade or parallelly couple these microring modulators or microring, let's say in this case filters or weighting, this is not weighting, but I'm showing on the filter. But if you have filters also in some architectures, then you basically, because of that crosstalk, the spectral overlap, you would say, of signals and neighboring microring passbands, you can have very high, depending on what is the channel gap that you're using, you can have up to 5 dB or in some cases even 9.7 dB power penalty at the modulator. And similar values for power penalty can exist at the filter as well. So the design parameters or design choices to sort of minimize this penalty would be the quality factor, the operating bit rate, and the channel spacing, right? But this still exists, right? And we have limited free spectral range of microring resonators. So to achieve larger number of wavelengths multiplexed per waveguide, we'll have to cram more wavelengths to in a given FSR to increase the finesse of the system. And that can lead to this high crosstalk penalties as well. So that's a limitation. The second limitation is, I would say, cross-weight penalty. The idea is when you have this cascaded microring weighting elements to create a bank, it turns out when you're trying to adjust the weight of one, let's say one particular microring weighting element, apologize for that, it turns out undesirably that particular microring can actually end up adjusting the weight of the neighboring channel as well. And that's basically referred to as weighting, you can say penalty, and the term used here most often is cross-weight penalty. And here is some analysis from some other groups' prior work that basically shows that this cross-weight penalty also basically depends on the channel spacing, and it could be up to 3 dB in some cases as well. So crosstalk penalty and crossweight penalty are 2 factors that basically incur some power. Basically, we can say loss or power penalty in the optical budget. The third is the high signal losses in silicon themselves. So if we talk about silicon, largely when we talk about the operation of silicon in O and C band, we don't worry too much about the losses. But it turns out because of the lower side absorption loss, typically, if the silicon is not doped, for example. But 2-photon absorption basically can really kick in silicon when we have a very large degree of wavelength division multiplexing, right? And 2-photon absorption, if 2-photon absorption basically can lead to sort of free carriers in the conduction band, then it can also lead to subsequent free carrier absorption, and that penalty can be significant. So if you see in this particular example where a regular channel waveguide, you can say 220 nanometer to 450 nanometer cross-section channel waveguide, was basically multiplexed. That waveguide had about 21 and 24 wavelength channels in that, versus when you had only one channel. So if you see the triangle plot, only one channel is there. If you see this, the circle plot here, the 21 channels and 24 channels for the square. And it turns out, compared to one channel, 3.3 dB extra penalty due to 2-photon absorption. And 2-photon absorption then leads to, you can say, self-phase modulation in the silicon channel waveguides. And this penalty is in addition to the nominal 2 dB per centimeter, let's say, or in some cases, maybe 1.5 or 1 dB per centimeter propagation losses of silicon waveguides. So this is in addition to that, right? So that loss also basically hampers, we can say, energy efficiency, and the way we show that, it also hampers parallelism, and we'll show how that exactly impacts the parallelism in the future slides. So all these losses and power penalties basically are related. They interact with each other because of a tight optical power budget, right? So the floor of the power budget is depends on the sensitivity of the receiver, right? It could be thermal noise floor, or maybe short noise floor, depending on what power ranges you're working on, and what is the noise level in the system. So that's the noise floor. But the ceiling of that budget, optical power budget, basically is not infinite, right? There is a maximum limit to allowable optical power, the maximum optical power that can be present for a waveguide, and there is a limit to power wavelength as well. So the power waveguide budget is typically set to 100 milliwatt or 20 dBm around that, because beyond that, given the small cross section of the 220 nanometer by 450 nanometer cross section waveguide, it turns out, if the power basically this is basically total power across all the wavelengths. If that increases beyond 100 milliwatt, it turns out the TPA plus SPM effect that we talked about in the previous slide, the losses because of that can go up to 6 dB or 7 dB as well in some cases, right? And that's a very large loss. So that's why typically the total power per waveguide is limited below 20 dBm. And when we talk about power wavelength also has some limitations in power. The main limitation comes from the peak laser output that we can have if you are using comb laser or a mono wavelength lasers. That can limit the power. The other thing is the power handling limit of the micro rings. Micro rings are basically can be multi-stable or bistable at fairly large optical input powers, right? So that basically also leads to sort of a lower ceiling for per wavelength. We call it that MOAP, maximum allowable optical power, right? So that basically gives us the budget, right? So we have the ceiling and the floor, and then all the power penalties and losses that we talked about, they basically have to fit in this budget, and they basically whittle down the optical power budget, and whatever remains of the power budget can then be used to support those wavelength multiplexing or spatial multiplexing or so forth, right? So certainly, if we have high losses, the number of wavelengths we can have will reduce, right? And that basically limits the parallelism. So we have basically shown, we basically call these two types of, we have basically these two categories we have already shown in the previous slide. The idea is we try to name them so that if you look at this sort of organization, if you see that you aggregate the wavelength channels first, so if you multiplex the wavelength channels first, then you have fan out, and then you modulate the input, and then you wait, right? So if you talk about the sequence, aggregate, modulate, wait. So we name this sort of organization as aggregate, modulate, wait. And you could actually aggregate, you can actually modulate first and then aggregate, and then you have fan out, and then you wait, right? So you have MAW. So these two categories of architectures, we looked at that trade-off, right? And this is basically more details on the modeling part is basically given in this paper from our group. but number of wavelengths per waveguide that we can have is a moderate value of 44, right? If you compare to that, let's say the resistive RAM crossbars, right? So you can actually have 128 by 128 size. When I'm talking about 44, we are talking about 44 waveguides and 44 wavelengths per waveguide. So it's a 44 cross 44. So compared to 128 cross 128, it's pretty low, right? And of course it depends on the speed also, right? What is the data rate and so forth. And the bit precision also, which is basically analog bit precision, also is very limited. 4-bit is what you can achieve. If you go beyond that, the number of wavelengths supported would decrease dramatically. So this is the trade-off, and we basically have, in last couple of years, we have looked at device circuit signal co-design approach to actually try to break this trade-off in many ways, right? So these are basically a handful of sort of publications that we have in this domain. And some of these publications basically look at the device circuit and signal co-design altogether. All three aspects are co-designed. For example, this bullet and this bullet over here. And some of the works are only looking at, let's say, device and circuit. And they are keeping aside the signaling, and signaling is still analog. So for example, this particular work, and we'll talk about, depending on what time allows us, we will talk about a few of these works. Next. So let's start talking about this first. So we already saw this trade-off over here, right? And the idea is reduction in let's say the parallelism, which is basically the number n, number of wavelengths per waveguide and number of waveguides in the tensor core. It reduces the system throughput, right? If you have a lower or smaller number n. It also leads to, basically, because we don't have a larger bit precision, it turns out you end up using bit slicing methodology to achieve larger precision for computing. That basically increases it increases the number of partial sums that you create. And then you have to deal with those partial sums, maybe optically in some case. In some cases, you will have to convert in the partial sums to electrical domain, and then you will have to basically deal with them using maybe electrical reduction network or reduction tree or something like that. So that also adds some more latency and energy consumption at the end. So it's desirable to actually push this value n, which is again the number of wavelengths and number of waveguides in the tensor core, as high as possible. If basically the processing is not limited by, let's say, the kernel size itself, right? Because in some algorithms, the kernel size is also sort of small. So if you have large tensor core, you will basically have some devices going idle. We have done that kind of work as well. So it has to be balanced, but the general approach is that you have as large parallelism as possible, and then you can basically reroute the signals if the kernel size is basically small, to sort of achieve a high hardware, you can say, utilization rate. But the idea is, if you look at it, this is again another representation of that budget, right? And if we talk about the bit precision, the higher bit precision would basically take up more analog levels in the optical budget, and the remaining green part would then part of that would be whittled down due to those penalties and crosstalk, and then whatever remains can be used for wavelength division multiplexing, right? And if you have a higher data rate, it turns out this analog resolution basically increases because of the noise floor, basically dependent on the operating rate, right? The noise floor of the photodetector. So if you talk about the digital, it turns out we only have 1 and 0, right? So we only have to support 2 levels. So that naturally gives us a larger sort of range available in the optical power budget to basically deal with the losses and then parallelism, right? So digital is favored, but we already talked about digital basically has some issues with some shortcomings about the area consumption and requiring longer latency, right? So we thought, could we do, we want to restrict to 0 and 1. We don't want to have multiple analog levels whittling down the optical power budget too much. So we thought we want to keep 1s and 0s, but then we don't want the binary encoding as well. So we thought, let's merge optical computing with stochastic computing. right? So we basically use DPU. Now DPU is basically dot product unit, which is basically another name of tensor core that we use frequently in the slides. Stochastic computing is basically an unconventional form of computing where numbers are basically represented by the probability of observing ones, right? So if you look at this, this is basically a stream or a vector of 8 bits, and there are exactly 4 ones there, right? So this basically represents 0.5 real number, right? And you can, and the position of ones in this 8-bit vector doesn't really matter. You can have like this, or you can have it like clustered together, right? That's the stochastic computing. So when you provide this stochastic bit string, let's say this is input, and you have basically encoded input in this sort of weight is encoded in this sort of a bit stream, and these are the real values of this. And if you pass this through AND gate, let's say, and you do bitwise ANDing, so 0, 0 is ANDed, then 0, 1 is ANDed, and so forth. So you will end up achieving this result. And if you see, you have 3 ones out of 8. So the result is 3 by 8. And if you look at it, this is actually multiplication of the I and W, right? So if you have stochastic computing, you only have to do bitwise AND of the input operands, and you can actually achieve the multiplication result. Of course, there might be some errors, and we'll talk about, we have actually dealt with those errors as well because of the stochastic nature. So you simplify the multiplication, you convert that into a simple bitwise logical AND operation, and the number of bits that you need in this vector or a bit stream can actually exponentially increase if you really want very high precision and accuracy in that case. So to the power, so if you have a bit precision, let's say you want 3-bit in terms of binary encoded, if you want a 3-bit precision, you basically need 2 to the power 3, so 8 bits in the bit stream. So we basically designed, of course, this is AND gate. We wanted to do optical, right? Electrophotonic, we can say, or optical architecture. So we basically made some innovations at the circuit device architecture and system level to come up with a tensor core architecture, right? So the first innovation was AND gate, which has been seen in prior works before, but we wanted to sort of repurpose the idea of creating AND gate using microring resonators here so that we could actually apply stochastic operands to them, right? So the idea is to have two PN junction-based phase shifters in the microring, the rim of the microring over here, and you also basically have to integrate microheater. And if you look at the spectra, so this gamma is basically where you will end up having the resonance of this microring because of the fabrication imperfection and all that. And what you want is you want to program that to eta position when the inputs I and W are zeros, right? When the inputs are zeros, you want to program that to eta. So you can basically just heat it up, right? You can operate the microring at a higher temperature to do that, to shift from eta, from gamma to eta, basically. So that is the idea over here. And when you apply the input operands I and W, it turns out, of course, you will have blue shift in the resonance. So when either I or W are ones, you basically end up having the resonance at this position. If you have both of them one, you end up having resonance at this position. And lambda in is the carrier wavelength. So with respect to carrier wavelength, if you look at the transmission, you would see that it actually follows the AND gate functionality. So we actually did this extensive, basically experimentally validated simulations to look at this. And if we apply the input and weight like this, you can see that the output transmission, the drop out transmission will basically follow the AND functionality over here, right? With some modulation amplitude, basically decision required over there. So, so we created you can say electrophotonic AND gate, and this can actually run very fast. We have done some analysis. I'm not included in the interest of time, but it can actually, this can run at 30 gigasamples per second, right? Gigabits per second, this microring. So we can basically run that at high speed. Now, the problem is typically it's not desirable to actually store the operands. When we talk about tensor core, of course, we need memory. We need to store the input and weight operands in the memory. It's not desirable to store in stochastic domain because I told you that the requirement of number of bits per, let's say, operand would go exponential, right? Depending on the bit precision that we end up having. So it's desirable to store the operands in binary. That means that now we'll have to convert those binary operands into stochastic bit streams or bit vectors before we can actually employ this to do a stochastic multiplication, right? Because AND gate can basically do stochastic multiplication. We discussed that earlier. So one way we thought of doing that was just simple lookup table based design. So the binary operand is accessed from memory, and lookup, the inference to lookup table basically gives us the stochastic conversion of those operands, right? And that would be parallel, of course, and then you use serializers to basically feed those stochastic operands into microring, and then you can achieve sort of a multiplier, right? So we call that optical stochastic multiplier, OSM, and we have basically symbolized that like this over here. So it can be lookup table based, and we have done some analysis, and we have created some sort of combinational circuits. The idea is, if we look at stochastic multiplication, by the way, we have done it for, it turns out, it's worth mentioning over here that the operation of this microring actually becomes polymorphic. It turns out if you basically can control the position of eta with respect to the wavelength, input wavelength, it turns out you can program the same device to operate as AND gate, OR gate, NAND gate, NOR gate, even XOR gate, and so forth. So it is really a polymorphic, and that is why we actually looked at the conversion. It turns out in stochastic domain, if you have OR gate, you can do all addition. With XOR gate, you can do actually subtraction, and multiplication we already seen, we can do actually multiplication using the AND gate. If you want to minimize the error, in some cases eliminate completely. If you want to eliminate the error completely, the requirement is that the conditional probability of X given W should be the marginal probability of X. The bit position should be created that way, right? So it's called the bit position correlation has to be there in the input operands to reduce the error to 0. So to achieve this, it turns out this can be achieved with a simple combinational decoders and some gates. So we can do that in parallel as well, and we don't have to rely on the lookup table. So it turns out the lookup table overhead, depending on what technology you end up using, SRAM versus DRAM, the overhead was basically large, and it turns out this combinational logic overhead reduces significantly. And we have done that analysis, we have done that comparison with other type of stochastic binary to stochastic converters as well. These are some prior works. And if we look at the area, energy, and latency product, it can be orders of magnitude, the benefits can be orders of magnitude higher for this sort of, you can say, combinational logic based deterministic stochastic operand generators, right? And I call them deterministic because we are basically deterministically controlling the bit position correlations among the input operands, right? To minimize the error over here. So, and the error also, the mean absolute error basically we get is about 4% in this case. And that error basically translates to not great degradation in the accuracy for the inference task of, let's say, convolutional neural networks or so forth. We'll try to show those results if the time permits over here. So, and then the other idea is, which is not innovation, but the idea is that we use a time integrating receiver instead of just regular TIA and then converting the results. So it turns out that basically gives us the analog accumulation capability, right? We can actually have a very large number of these bits being accumulated at the time integrating receiver, right? And we can have basically incoherent superposition as well. So across wavelengths, right? Because the photodetector would work as a multilinear map across wavelengths, right? Anyway. So we use that to sort of now count, right? We have to also convert the stochastic bit stream. We have done the multiplication using the optical AND gate. Now we have to, what we do is we basically count all those ones, and then we accumulate those. So we convert the counting of ones into analog quantity, and counting of ones basically converts the stochastic number to analog number. and so forth. And we can basically then organize this optical stochastic multipliers in a tensor core arrangement like this. We can have filters to control the negative computation as well over here, like that. And we can create this tensor core. And of course, yeah, so it turns out we could actually increase the parallelism to 176, right? And the idea is that in this case, the FSR was basically really considered really high. But even if the FSR is lower, we can still have significant parallelism compared to the 44 that we are achieving like in the analog, right? And the operation can be 30 gigabits per second. And the precision really is flexible in stochastic because you can have the same multiplier, and if you change just the number of bits in a vector, you can basically have a larger precision or a smaller precision. So you can really program the precision over here. We don't have the programmable precision results as of yet, but we'll see if we can show those results. So we have done system level evaluation, of course. The code is also available on the GitHub. You're free to basically look at that. So we have frames per second for convolution neural networks is what we did this. We have sort of frames per second per watt and the density as well over here. And because of the stochastic nature, we have, of course, accuracy drop, but it's not significant. Top 1 and top 5 numbers are basically reported over here for this architecture. So that's you can say, of course, device, circuit, and sort of signaling, right? Signaling is stochastic sort of co-design. Now, we also looked at I'll try to quickly go through this idea. It turns out the way we organize this tensor core also basically impacts the parallelism or the size of the tensor, achievable size of the tensor cores, right? So we have looked at that as well. We have actually analyzed different. So we basically classify. We saw the two kind of classifications. So we have basically tried to expand that. So in tensor cores, typical, you can say, manipulations of signals. There are 4 types of manipulations that happen. You basically have splitting of signals, which basically is fan out. You have aggregation, which is basically fanning or multiplexing. You have modulation of input values. Then you have modulation of weight values, which is basically termed as weighting, right? And then you basically have sum the optical signals. These are the 5 top type of manipulations that you need. So depending on the order in which these manipulations appear from, let's say, starting from the laser to the summation element, right? Depending on the order these manipulations appear, you can classify different designs, right? So we have already seen this. This design would be, you would say, aggregate, then split, then modulate, and then weight, right? You aggregate first, then you split, then you modulate, and then weight, right? And then you sum. So this is the order in this particular design. If you look at this design, you have modulation first, then aggregation, then splitting, then weighting, and then summation. So you change the order a little bit, right? Now you can actually design a spectrally hitless architecture. So if you see, these are basically cascaded microring banks, right? So you can create a spectrally hitless where in a waveguide, you only have one wavelength, and the neighboring wavelengths and neighboring microrings don't actually interfere spectrally as much as possible, right? So you can have this sort of spectrally hitless design as well, where you end up splitting first, right? Then you basically modulate, then you weight, then you aggregate, and then you sum. So that becomes the order in this case, right? So the ordering basically changes, and depending on the ordering, it turns out we can basically the losses that appear. We saw the different type of losses in the organization. So we basically name this organization depending on the order now. So we term them ASMW, MASW, and SMWA, right? And if we talk about propagation loss, you would say that the propagation loss in SMWA would be very high. This is SMWA, by the way. So why? Because of the spectrally hitless design, you end up having long accumulation waveguides and long sort of distribution waveguides, right? So the propagation loss ends up being high in these cases. In this case, right, you will have a very low loss here and a moderate loss here, right, of the waveguides. So similarly, you can say that through loss also basically typically occur in these blocks, the modulation block, aggregation block, and weight block. And if you look at it, the through loss will be highest in this sort of design, and lowest in this sort of design. Why? Because you don't have sort of out of band through loss in SMWA, but you will have the out of band through loss highest amount in ASMW design, and so forth, right? And if you talk about the insertion loss of devices themselves, right? So for a wavelength, right? If you look at it, so every wavelength will look very less number of, will have to pass through very less number of, let's say, active devices in this case. So that's why SMW will end up having very low sort of insertion losses versus the other designs, right? And so forth. So those are the losses. If you talk about the power penalty, like intermodulation crosstalk, that intermodulation crosstalk would occur at the modulator banks, right? The crossweight penalty, of course, will occur at the weighting bank and so forth, right? But if you talk about this SMWA design, because of the spectrally hitless design, you don't have intermodulation crosstalk or crossweight penalty. But what you have is when you aggregate, you will have those filter penalty in this case. So you do have filter penalty in that case, but the absence of intermodulation crosstalk and crossweight penalty actually gives us some benefits in that case. So if you explain that, of course, all this, it should be clear now that these organizations, they basically, the trade-off that we looked at, the precision and the size trade-off would basically change across different organizations. And we basically did this analysis, and it turned out the SMWA, which are these triangles, had a very high basically wavelength. Compared to 44, we could actually achieve close to 100 in this case. And we can have FSR limited region is over here, right? So we can have a very large bandwidth or parallelism over here, right? And we did some system level analysis of these organizations as well. And we came up with the wavelength parallelism and waveguide parallelism numbers doing this analysis. And we showed that obviously SMWA will basically achieve high throughput compared to other designs over here. So that's this work over here. The next, we basically looked at we thought, okay, we looked at the stochastic signaling, we looked at the analog signaling, but in analog signaling, it turns out one of the challenges that we basically don't realize, like just on the face of it, is that the weighting banks are more basically, the control circuit is much easy to design if the weighting banks are thermo-optic, right? So thermo-optic weighting bank basically gives that constraint of speed on that. It's going to be very low speed. So we cannot change the weight of the weighting bank too frequently. So all these designs basically end up using sort of, you can say, weight stationary data flows, right? The weight becomes stationary in this case, right? And we wanted to change that regime. Of course, people will say we can do electro-optic weighting as well, but it turns out the electro-optic weighting of already modulated optical signals, the control of that becomes very basically complex, and it has been hard to actually prototype such weighting so far by the community, right? So we thought this is an idea. We are basically working on fabrication for this for now, but we have actually done extensive simulation analysis, and we have published this in this publication. The idea is to use hybrid time amplitude analog signaling, right? The idea is to have, let's say, the input represented as, you basically create pulse width amplitude modulated electrical pulses, basically. And you, if you take the input is encoded as the width of the pulse, and the weight is encoded as the amplitude of the pulse, right? And that pulse width amplitude modulated electrical signal can be basically then applied to the microring directly. And then the microring will basically generate a balanced, you can say, input, right? So if you look at this, these are the input widths of, so this is the A over here. So you encode the input in the width of the pulses over here. And here you encode the input in the amplitude. So the weight is basically encoded as the amplitude. And if you have some threshold below this threshold, the result from the micro ring will basically go to the drop port, and above this threshold, the result will go to the through port, right? Because you're looking at the difference in drop port and through port transmission, the micro, right? And then you can have this time integrating receiver at the end. So if you have a time integrating receiver at the end, you can actually operate that in a multiplier mode as well, where you basically operate this TIR circuit or a receiver circuit at the data rate speed, right? Then you can basically have multiplication results coming up, right? You multiply, because if you see, this would be a pulse width amplitude modulated signal, right? So if you look at the area under the curve of this signal, that area will basically represent the multiplication result, and that area can be transduced into the voltage by using a TIR over here, right? So you can basically do that you can operate this circuit in a multiplier mode, or if you basically the sampling rate is way slower than, let's say, the operating data rate over here, then you can operate that in a temporal accumulator mode as well, and you can achieve a temporal accumulation result at the end over here. So this is one device that we created basically. And we basically did the crosstalk analysis when we basically cascade them to sort of these devices over here. And we did analyze the calibration accuracy. And it turns out about 15-bit, close to 15.3 is what we have, this color over here. So 15.3-bit accuracy, calibration accuracy can be achieved. And if you look at the crosstalk over here, the green dots are this sort of arrangement. And the red dots are basically the arrangement where you have a separate modulator micro ring and a weighting micro ring. So in that case, you will basically end up having 4 micro rings over here. So the crosstalk and other power penalty is basically reduced. So what you want to look at is that if the dot is closer to the origin or not, closer to this cross-section point or not origin, but the cross-section point or not. So the green dots are closer to the cross-section point, so they basically have a smaller crosstalk compared to the red dots in most cases. So we did this, and then we created this sort of a tensor core, which is again a spectrally hitless tensor core, right? You have a comb source coming, throwing the lasers. You basically have that fan out. You have the wavelength channels coming in these waveguides, and then you can basically filter individual wavelengths, and you can have this, we call this a TAOM, time analog amplitude modulator, optical modulator. So you can have a spectrally hitless design. And it turns out we did this scalability analysis, and it could be about 2x the purely analog design that we looked at, right? We can achieve 83 as the number of wavelengths and crossing, right? So the size. And we had only 44 in purely amplitude analog design. So this is what we have done. And then lately, we have also looked into, so we discussed this, the shortcoming of silicon, that we have, let's say, the 2-photon absorption and self phase modulation issue in the silicon. So we thought the industry, the academia, the field, the research field has the answer to this. Like, we can use silicon nitride to actually not have 2-photon absorption, because silicon nitride doesn't have free carriers, right? Typically. So we can use that to achieve, to get rid of this shortcoming of this. And so we basically said, if we have silicon nitride and we try to create a tensor core out of that, how do we achieve that? And with that, we basically thought, okay, if you're creating a silicon nitride, the waveguides are silicon nitride, then it might help to actually have an active silicon nitride modulator and a weighting device as well. Silicon nitride material is not active, but maybe you can basically have heterogeneous integration of active materials on the cladding and then achieve that. So you can have everything on the silicon nitride platform, sort of, right? So we basically use indium tin oxide and the high refractive, electrorefractive activity in indium tin oxide to actually create a silicon nitride indium tin oxide hybrid micro ring modulator. And we could use that as a weighting element as well. And we created this, again, spectrally hitless design. So in the first design, we have only done like the all pass ring configuration over here. This is how we basically ended up doing it. And it basically employs this high electrorefractive activity of of ITO. So this is the Drude Lorentz model that can basically show that at some frequencies you basically have very high electrorefractive activity in ITO. And this is true for other transparent conductive oxides as well going forward. So we did this analysis. We could basically achieve 18 nanometer FSR with 450 picometer per volt modulation efficiency. The peak voltage required was 9.2, it's a little bit on higher side. This case, the insertion loss was also low. The Q factor, we couldn't achieve a larger Q factor. 2000 was what we could achieve, and the excitation ratio we achieved was like 8.2 dB, right? And we could use that as a weighting microring as well at the throughput microring. And for negative results, again, we could basically use active filtering if the result of the sign of the multiplication result can be basically pre-processed, then we can actually change the transmission, and we can basically achieve the subtraction as well that way. So we actually fabricated this. This is the passive microring silicon nitride, and this is the active with the ITO heterostructure on top of it, as you can see at the Argonne National Laboratory collaboration that we have. And then we did some system level analysis. Again, the same set of equations we will end up seeing, but you would see the difference here in terms of the silicon losses, and these are the nonlinear losses and the nitride losses. And you will also see the propagation loss difference over here, 1.5 for silicon and 0.5 dB per centimeter. This is basically still conservative, right? It can go lower than that, and we can have larger benefits if we can go lower than that. And you would see that you will have about 1.5x more basically multipliers you can have, parallel multipliers in this design compared to, let's say, silicon-based analog design, right? This is in comparison with silicon, or we can call that silicon non-insulator SOI design. So we did system level analysis on this as well. And silicon nitride basically ended up giving us better throughput, better energy efficiency, and so forth. So with that, the outlook for my research so far has been, we only talked about electrophotonic, but my research also focuses on DRAM, computing acceleration, and also spin lattice, the ferromagnetic spin lattice for neuromorphic computing. And the idea is to reach there, we can say 1 beta operations per watt. That is what we're trying to achieve with flexible precision, if we can overall in the lab. And what are the ongoing work? So we have actually extended the ideas. You see all the analysis, the system level analysis results that I've shown, they are only focused on convolutional neural networks so far. We have already started looking into more basically scaled architectures like transformer neural networks, and we have some results, and the results will be published soon. And we have the fabrication and prototyping funding, and we're trying to basically prototype that hybrid time amplitude analog modulator, and also the stochastic tensor. It will be a very small tensor core, maybe 2 microrings based, but we are basically working on that on silicon, by the way, and we're looking for motivated students and collaborators for that. So I would like to thank my basically collaborators and research sponsors on that. And with that, I'll end my talk today. Thank you so much. We're happy to answer the questions.
Yeah, thanks very much, Ishan, for the great talk. And we do have multiple questions in the chat box. I'll moderate the Q&A section. For example, I think the first question from TQ, stochastic computing with optical computing is very interesting. Are you aware of any hyperdimensional computing? Would it be possible to combine it with optical computing? Yeah, can you comment on this and share some insights?
Most certainly, why not? I'm not aware of anything, but maybe we can collaborate to explore that. So I'm at least aware of this fact that in US and largely, I think there are not a lot of works that have actually combined stochastic computing and optical computing together. So certainly the publication that I talked to you about was the first one in that domain. and hyperdimensional also can be done. And with the polymorphic design that I talked about, right? If you look at it, if I have some results, yeah. So this micro ring that I told you about, right, which can function as AND gate. So we can just operate that as different gates as well. All we need to do is just basically program the relative position of input wavelength and kappa over here, right? And we can basically operate that polymorphic. It's polymorphic, so certainly we can use this to do sort of the hyperdimensional operations that we need, right? So yeah, certainly possible. Please reach out if you'd like to collaborate on that.
Yeah, great. Yeah, as for the hyperdimensional computing, I noticed probably several years ago there might be one paper or something talk about optical hyperdimensional computing. Not a lot.
I think was it from yeah, I might have looked at. I'm not exactly sure what group was that, but I think it was coming from the angle of, I think, the content addressable memory, right? So it was optical content addressable memory and use of. I'm probably familiar with what you're talking about, but I cannot pinpoint the exact work. And yeah, if you know, yeah.
I thought like hyperdimensional computing probably requires tens of thousands of dimension. Maybe they're using like free space diffraction. I cannot remember exactly.
Probably, yeah, probably. And when you say dimension, we are talking about vectors, right? We can create a 10,000 long vector, right? 10,000 bit long vector. That vector can be operated serial, right? Because we have gigabits per second, and you can operate that serially here, right? So that works. Latency will be something that we'll have to deal with, but if we can achieve parallelism, that's what the optics is about, right? Then maybe there is a case for really efficient hyperdimensional computing framework here.
Yeah. The second question is from Zhengqi. Generally, there are two schemes mentioned today, digital and analog optical computing. They have their own pros and cons and challenges to overcome. Which would, Professor, you think be more promising?
It has to be a hybrid, to my understanding. So some of the ideas that we talked about, stochastic is basically, you would look at it, it's sitting in between. So stochastic numbers, you can also think of them as quasi-analog, right? So especially if you look at, it's quasi-analog, you can think of it, because it's sort of time analog also, you can say. Sorry, yeah. So if you do stochastic this way, then you can think of that as the analog time, right? Encoding, because you have 4 bits. So for 4 time periods, you will have 1 and then 0, right? It's called transition coded, right? So it's a quasi analog, but you only have ones and zeros. And it's a separate from analog time, because you are not really looking at the pulse width. You are basically have individual bits, and you can actually achieve multiplication just by AND operation over here. So I think it has to be, you have to balance the pros and cons of both sides, and I think it has to be mixed signal going forward.
Another question, also about stochastic computing. Is it possible to leverage and manipulate some on-chip noises for this random sequence generation and can use it for stochastic computing?
Yes, certainly. So if you look at, I have not given more information on that, but if you look at, these are the methods that are typically used or more popular to convert binary into stochastic. So conversion, stochastic number generator basically requires random or pseudo random number generators on chip. If you don't need to have sort of deterministic bit position correlation, right? So we can use the noise, but then the numbers that you generate out of that noise will not have this deterministic bit position correlation that you need, especially in multiplication, subtraction, and addition, to eliminate the error or minimize the error, right? So I think deterministic approach, if you want to do stochastic arithmetic, deterministic approach would work better for error reduction than, let's say, pseudo random or random approach. But in general, stochastic number generation requires if it's not for arithmetic, right, for some other reason, maybe for security purposes or something like that, requires pseudo random numbers or random numbers. Yeah.
Yeah. Yeah. Along this direction, only seeing one word probably leverage this on-chip noise as the latent variable for optical GAN, like generative adversarial network. This is the only word
Oh yeah,
from Duke or
one
for this. Okay, the next question is like for other architecture using the pulse width modulation. So how fast and efficient is this pulse width modulation module, basically?
That's great. So we have only operated at 1 giga samples per second because we also had to basically allow for the pulse width to be changed, right? So that's what was the shortcoming there. So if I look at that, we have actually so far looked at the calibration accuracy over here. Calibration accuracy can be 15, but in this particular fashion of designing is again not devoid of crosstalk and other issues, right? But if you can create spectrally hitless, this can operate at 1 giga samples per second, right? And we have the system level results. I've not included them over here, but you're welcome to look at the publication that I basically put there. So it can be accurate. Yeah, we have not done more than 4-bit precision for that. The precision tends to basically be diminished because of the crosstalk and other issues, the regular noise and crosstalk issues in analog computing. But the advantage is the parallelism increases. The main idea, even in this domain, you would see that every signal will have to pass through less microrings in this sort of organization, right? Because there are 2 microrings only. Versus in the other case, when you have separate modulator and weighting elements, you will have 4 microrings. So 2 will be in band and 2 will be out of band or a wavelength, right? In this case, versus here, it's 1 out of band and 1 in band, right? So that basically significantly reduces crosstalk and power penalty and all that, insertion loss and everything, right? And that is what basically gives us advantage.
I see. So for this architecture, you're using the output stationary integration-based method, right? So here is an integrator. So typically the output dot product results will passing through some sample and hold because for high-speed signals, analog computing, the output waveform will be like a little ugly, right? So you will find the middle point, sample it and hold. So you can have a square shape and do a integration, right? You get the area under the curve. But now you modulate the pulse width. So how does that work with this sample and hold integration?
Yeah, that's a great question. So it's based on simulation so far, and we've done all of that over here in the simulation. And it turns out you basically have to calibrate, obviously, right? So you will have those peaks, and I can show you some sort of peaks which we basically observed in the weird, as you're talking about, like the area under the curve is not cleanly rectangular, right? Obviously, you will have, if you look at this, so you will basically have some not truly rectangular. This is still pretty rectangular, but not truly rectangular, basically pulses, right? And you will have to basically calibrate the area, the analog voltage that you get out of it, right? And that based on that, you basically have to decide what you want to keep the operating data rate as and what should be the widths, right? So coming back to this, the width wise, we basically tried, sorry, what is the accuracy results? Oh yeah, going back. Oops. Okay, here, sorry. Yeah. So if you look at it, we basically looked at different, this is the highest pulse width that you can have, right? So if highest pulse width basically means that if you have a 4-bit, let's say input, because input is encoded as the pulse width, 4-bit input, then 4-bit input, basically the highest would be like 48 picoseconds wide, right? And 16 picosecond, it's not highest, sorry, 48 is the one step. So the highest would be 16 times 48 picoseconds. because 4-bit is basically 2 to the power 4. So 16 basically unit time periods you need. So 48 picosecond times 16 would be the highest pulse width. So that basically drives your operating bit rate, because the non-idealities that you talked about, the sample and hold noise and all that, basically also depends on the operating bit rate. And this is not going to be weight stationary, by the way. I would like to point that out. And unfortunately, we'll have to look at this paper again, which is just accepted, by the way, this one. Not this one, sorry, the previous one. We call Hyana, right? So, which is basically the final. We have put that as on the archive, but it's, you will not find it like at the publishers. So we have put that on the archive. But if you look at this paper, the archive paper, it turns out we can actually have the input stationary and output stationary as well. How do we achieve that? So if you look at this figure, it turns out we can basically, it's a fast 1 gigasample per second, both input and weight are covered there. So there is no need to wait longer to actually encode the weight, right? So it's not basically limited by the speed of the weighting element here. So we can actually change the values as we please. And then if it is not output stationary, let's say it's input stationary or something, then what you can do is you can actually change the accumulating capacitor. And so there is a bank of capacitors that you can use, right? So you can actually accumulate in situ a large number of bits, right? And there is enough prior work. If you can basically control the noise, you can easily have thousands of basically this multiplication results, which are the pulse width amplitude modulation symbols. You can accumulate thousands of those before you basically reach the saturation of TIR. So you can actually do in situ partial sum accumulation as well. So that is the advantage of this as well.
Okay, yeah, thank you. We have 2 more questions. Another one from Rina Huang. Is the ITO silicon nitride micro ring offered at any silicon photonic foundry right now?
No, this was not. Yeah. So ITO is a very bad material for CMOS compatibility, right? Because it does degassing, that they basically causes degassing issues in the instruments, and it's very bad. So ITO, people go away from ITO. They wouldn't want it in the vicinity of the regular CMOS. So this was done at the NanoFab facilities we had access to Argonne National Lab.
Let's see. Another question about the silicon nitride micro ring. How fast can this ring switch? Because the tuning voltage is around 9 volt. Generating a 5-10 gigahertz 9 volt signal will be challenging.
It's a great question. So we didn't run it beyond, I would say, 500 mega samples per second. We couldn't do it faster than that. This one. And the voltage is high, but it doesn't actually result in a lot of capacitance. That is the advantage of this. Okay, why? Because you basically have a capacitor structure at the here. If you see the hetero structure over here, so it turns out the capacitance is not that large. The voltage is high, but it doesn't have to drive the capacitance that large. So the speed is not really low like in kilohertz. We can still achieve some megahertz speed here. Yeah.
Okay, great. If there are any more questions from the audience? Okay. Yeah, if no, let's thanks our speaker for the great talk. It's really in-depth research, especially on the micro ring-based optical computing, covering all the aspects. And also thanks everyone for joining the seminar. We have definitely more offline discussion for the audience. If you do have good ideas to collaborate, feel free to contact Ishan separately. And
Yes.
and slides and video.
My
Okay.
information. Yeah.
Oh, that's great. Yeah, this is the Ishan's contact. Okay. And record the video and slides. If the speaker agrees, will be online, posted on our website and YouTube channel shortly. And please also share with your friends who cannot attend today. And welcome to subscribe our mail list and please follow our future seminar events. Okay, I think this concludes today's event. Thank you everyone for joining, and also especially thanks, Ishan. Very nice to have you today.
Thank you. Thanks, Eugene.
Yep.
Oh, somehow I'm not able to end the call. Why is that?
Okay.
Okay, I can now. Okay, sounds great.
Okay, great. Yeah, thank you everyone. Yeah, bye.